I should know. Remember the two basic functions we did here? Okay, they saw a bunch of others in the homework, but the 1 over x and the 1 over x squared. Remember, all the things you need to know to evaluate these numbers. And once you got the numbers, you do the finals, draw up the graph. Okay, so looks good. One thing about this is you notice I didn't include 0 in here. So question is, what would you do with 1 over 0? So now we see the trend over here. Our basic function tends to go up because we have positive numbers, positive values of x. Okay, tends to go up if you get closer and closer to the y-axis. It looks like it's going to keep going up. It doesn't come through the y-axis and wiggle on down here. It's separated into two pieces. And there's a piece over here that goes up, and if you continue the graph, it just keeps going up and up and up. Keep getting closer and closer to the y-axis, but it never gets there. And there's no limit to how high it'll go. Okay. If you go out here, it's going to start leveling off, and it's going to do the same thing with the x-axis. No matter how far you go, it's never going to hit the x-axis. But it's always going to get close. Matter of fact, every time you go 1 unit, it gets twice as close. So if we get twice as close to another unit, we're going to be this close. To another unit, we're this close. To another unit, we're this close. Pretty soon, my fingers are going to touch because I can't make it infinitely close. Okay, there's a limit to how close I get without having the things touch. But the thing keeps getting closer and closer. Won't take all that long before it's closer than 2 atoms. Okay, see how long would that take? It's got to be 10 to the negative 10th meters. Right here, it's about 10 to the negative second. We got to go 10 to the negative 8th. Should be 10, 20, 30, 40 units from here. Going to be within an atomic time. 40 units, that's like a little over an inch. Okay. So you get out there 10 feet, and this graph is going to be down to less than an atomic diameter, okay, of the x-axis. And it's only getting started because it's got a long ways to go up there. You can go miles and miles. Go to the moon. Move that way. That's okay. So it's not too hard an idea to wrap your head around, but let's see how the numbers work. A little exercise with some arithmetic, okay? So got y equals 1 over x. And what I said is totally wrong. If you move 1 unit, it doesn't get that much closer. That's 2 to the x function. So apparently, I still got turkey in the brain. Okay. Doesn't approach that quick. The exponential function does. We've got to take a look at that too. Okay. 1 over x function has a characteristic that if you move twice as far, you get twice as close. of the x-axis. When I say twice as far, it's implicit from what I just said. Twice as far from the y-axis, you get twice as close to the x-axis. Okay. That means pick any point. We'll just start here. Okay. How far is that from the y-axis? Well, this far. How far is it if it's twice as far? It's out here. Here's twice as far from the y-axis. It gets twice as close to the x-axis. Does that make sense? Okay. Then you move twice that far from the y-axis. So you move out to here. And you're going to get twice as close to the x-axis. So twice as close to the x-axis. Be from like this far to this far, twice as far from the y-axis, like this. Okay. So do a quick sketch of this and show me the next point. Okay, now getting our heads around this, this is just a geometric look at the way this function behaves. Okay. I said we go twice as far. Start here, we go that much further. Then twice as far is this far. This is how far we are at this point, and we move that much further. Then twice as far as this, we have to go out here. So each point is twice as close to the y-axis. Okay. The y-axis, here we are. We move twice as close, still have pieces here. And we move twice as close, that puts us here. We move twice as close, that puts us here. Okay. So we don't want to mark off a bunch of points. We don't even want to put numbers down. We just do it geometrically. We don't know what the unit means. Okay, like the unit might be 10,000 miles. Okay, if we're looking at the way gravity acts with the moon, or the way, in this case, potential energy. Okay. And you don't need to understand the physics of that, but it's kind of neat. And then over here, we can mark this distance, the x-axis, and then half that distance, and then half that distance. And the familiar idea of subdividing in equal subdivisions. Okay. So each of these points is twice as close to the x-axis as the one before, right? As the one above it. So now we can locate this point, we can locate this point, we can locate this point. We don't need numbers and calculations to draw the graph now. We draw the shape of the graph just fine by doing this. Okay, so we go out here to twice as far, and we got to be twice as close to the x-axis. Get this. Now to get twice as close again, as opposed to what I told you a couple of minutes ago, I wasn't thinking, and hopefully I'm thinking now. Okay, we go twice that far, we get twice as close. Okay, now to get down within an atomic diameter, we're going to have to put flip-flops. Okay. I don't have room to go twice as far now, so we'll just have to take it on faith. The graph's going to continue like this. Well, and this part of the curve here corresponds to what you see here. Got the same shape. I mean, it might be stretched out that way a little bit or compressed down or whatever. Okay. But it's got the same fundamental shape and the same characteristics as this graph. Okay. Except now we see how to extend it. So there's algebra. involved with this whole idea. Okay. How do you know if you move twice as far, you get twice as close to the x-axis? Okay. Well, if you divide one by a number, you get something, right? If you divide one by a number that's twice as big, you get a number that's half as big. Okay. A number twice as big goes into one half as many times. Okay. So let's say instead of one, this is 1,000. Okay. Divide 1,000 by 10, you get 100, right? Divide 1,000 by 20, you get 50, which is half as much. And yeah, maybe I'm going to use these as well. Divide 16 by 2, you get 8. Okay. And what's twice as big as 2? 4. Divide 16 by 4, you get 4, which is half as big as 8. Now, I might or might not understand that from my saying it, but let's look at this. Okay, so well, now I got myself in a little bit of a box. I don't really want to talk about classes, see if I know it. So I'm just going to go to some algebra. Okay. It's actually an algebraic proof. I actually do a lot of proofs, but a proof is just a way of writing it out that convinces you that it's true. Okay. Okay. X2 is a number, X1 is a different number. X2 is twice as big as X1. Okay. Then what's 1 over X2 divided by 1 over X1. Now, whether you totally understand the argument I'm making, all of a sudden here we've got fraction calculation to do. I'm going to ask you to do. Okay. Now we've got just a little bit of a question here, but first, 1 over X2 divided by 1 over X1 is 1 over X2 times X1 over 1. And you multiply numerators and you multiply denominators. So that's how you multiply fractions. And you get X1 over X2. Okay. Now there's a question. Are these like terms? Okay, it's a very good question because you probably haven't seen subscripted variables, but X of 1 and X of 2 stand for totally different things. They're related because of the way I've defined the relationship. Okay. But the reason we often use subscripted variables is because there are only so many letters. And really we want to think of X as being the number along this axis and Y as being the number along this axis. So it could be that if X2 is equal to X1, then we would say, well, if this was X1, where would X2 be? Well, it's twice as big as X1. So X1 is here. Where's the number that's twice this big? Let's talk about that for a second. Okay, so along with that question, okay, if X1's here, where's X2? Now, what I've asked everybody to do is, I'm just going to kind of move along the x-axis.
Right there.
And you. I said, what you need to do is jump up and down. Okay, guys, don't do anything with your voice. Okay, but that was a guy out in the hall. Okay, now, and before you're jumping up and down, don't get in front of the camera. Okay, got to protect privacy here. Okay, so here we go. Ready? Okay. Okay, you didn't jump up and down, but you raised your hand. I think that's pretty good. Here's how far this is. Oh, you nailed it. Okay. Yeah, you were going to be a little bit late, weren't you? Oh, well. But you're at a different angle with the board. I use that for an excuse when I get my writing going down the board or out the board. Okay. So you've got an excuse. See, you were straight on it. You couldn't have missed it. Okay. Well, there it is. Okay. Here's X1. Here's X2. Now, how close are we to the x-axis here? This is how far we are, right? And how far are we here? Well, we're down about here. About twice as close. Should be. Graph isn't quite right. This point maybe should be lower. My x-axis is kind of got a little wobble in it here, so it's a little higher than it should be. So the graph isn't great. So, okay, so now my question is, okay, don't say it's just if we divide 1 over x1, well, let's say if we divide 1 over x2, which is this, right? By 1 over x1, which is this, what are we going to get? Okay, what we're trying to get our heads around here is that we're dividing one of these numbers by the other, okay? Now the number we're dividing into is this one. So it's this, right? Because there's your 1 over x2, because x2 is twice as far as x1. Okay. It turns out then that 1 over x2 is half as big as 1 over x1, isn't it? So we're dividing something that's something here by something that's twice as big. If I divide a number by a number that's twice as big, what do I get? I get 1/2. Divide 4 by 8. Well, that's 1/2. It's meaning of the fraction. It's trying to make a little bit of geometric sense out of these numbers and connect it to the algebra. Because in pre-calculus, you do a lot of work connecting pictures with algebra. And usually you start with the algebra and make the picture, but a lot of times you want to be able to look at the picture and figure out the algebra. Okay. Okay, so the bottom line here is this is twice as big as this. We can see it. It's twice as big as this because why? Because this is twice as far from the x-axis as this. And if what I'm saying is true, there we have it. Now I'm kind of twisting the logic around here a little bit, but I'm not too worried about the logic. It's the whole picture and the whole idea. Logic of the proof is if x2 is twice as big as x1, then if we divide 1 over x2 by 1 over x1, we're dividing a smaller number by a bigger number. And the bigger number is twice as big as the smaller number. So that ought to be 1/2. So from this picture, 1 over x1 is twice as big as 1 over x1. So if you divide 1 over x2 by 1 over x1, which is twice as big, you should get you should get 1/2, right? Okay. Now over here, is this equal to 1/2? Well, I'm going to ask you to figure that out for me. Can you plug in 2x1 for x2? In other words, x2 is 2x1, so replace x2 by 2x1 and see what you get. Okay, so what we're doing is we're replacing x2 by 2x1. Because x2 is equal to 2x1, I can put 2x1 here. Replace x2 because they're the same. Okay. So with x2 equals 2x1, so I can replace x2 by 2x1. Well, how do you simplify x1 over 2x1? X1 over 2x1 is just what you get if you multiply 1/2 by x1 over x1. Now we got x1 over x1 here. And what's x1 divided by x1? Just demonstrate this. Yeah. Okay. So that's 1/2. Okay, now the subtleties of any logical argument are beyond what I'm really wanting to accomplish here. It's a little unrealistic to accomplish that at this point. But the reason I do this is to show you how the algebra works along with the shape of the graph and the geometry and the nature of the function. Okay. Now what we've just done is we've proven it doesn't matter what x1 and x2 are. As long as x2 is twice as big as x1, this is what we're going to get. Which justifies what I said before. We can construct this graph by moving twice as far, then twice that far, then twice that far, and going half as close to the x-axis. Okay. Every time we move twice as far on the x-axis, we get twice as close to the x-axis. Okay. Now there's a big point here. This shows that we're always getting twice as close. And well, you know, there's a ledge here. I don't want to step over the ledge. And I'm going to fall 6 feet. At my age, you don't want to fall 6 feet unless you're really relaxed. Okay. So I'm going to move twice as close to that ledge. Then I'm going to move twice that close. Then I'm going to move twice that close. Okay, when am I going to get to the ledge? Well, let's talk about it. Okay, got a quick answer to that. The question is, when am I going to get to the ledge? Never. I'm going to stay safe forever. Might starve to death, but I'll stay safe. Okay. When am I going to get to the x-axis if I keep doubling the distance and go twice as much? Never. Okay. Since he's never going to touch the x-axis, that's the nature of an asymptote. It's something people have trouble in pre-calculus grasping. They can quote it, they can say there's an asymptote, and very seldom really understand it. And it comes about, along about 10th week of the course. Okay. But there are asymptotes right at the very beginning of these functions. And now let's think about what happens as we get closer to the y-axis. So let me ask you to construct another one. Here's the point on the graph. Actually, I'm going to move the point on the cursor. There's a point on the graph, not too far from the y-axis, down real close to the x-axis. Okay. Now, what's going to happen if I move twice as close? Where's the point going to be? Show me your paper. Now, twice as close would be here. We're used to subdividing the interval. Okay. Now we go twice as close to the y-axis. That's going to put us here. We're going to go twice as high. Well, let's go ahead and mark off projection line here to show how high this point is. Now we're going to have to go twice as high, so that's going to put us like here. Going to get to the point here. Still pretty close to the x-axis. You go twice that close. Then we're going to have to go twice this high, which is going to put us up here. Now we're starting to get somewhere. So we go twice as close again. We got to go twice this high, which puts us up here. And we go twice that close. I don't know if I can do with this chalk. There, that came out pretty well. I don't know if you can even see it, but really good. Okay, well, came out better than I could have expected. It's going to go twice as high again. Well, now if the y-axis is here, this point is going to be really close to the y-axis. And with the chalk, I'm not going to be able to get much closer. But you can still think of the idea if these are real, actual geometric lines with no thickness. This thing's going to get almost vertical, but it's going to keep going twice as close to the y-axis. I have to go twice as high, so it'll be up here somewhere before we can get twice as close. But if you continue this, because again, just like me trying to avoid stepping over the ledge by always going halfway, you're never going to get to the y-axis. So you're always going to be doubling your distance up here. And we move closer to the y-axis twice as far. Well, by the time we're up here, maybe a foot high. Okay. I go twice as close 10 more times, we'll be over 1,000 feet high. But twice as close 10 more times will be 1,000,000 feet high, which is like 200 miles. Okay. And just 20 more times, going closer. Okay. And then 20 more times going closer to that will be at 200,000 miles, which is almost 240,000 miles roughly. Okay. And after that spacecraft is over. Now, we say the spacecraft is orbiting the moon. We can use the reciprocal square function. Okay. We can use the reciprocal square function to figure out from how close the spacecraft is to the moon. Right now, it's about 260,000 miles from the moon. Okay. That's our 260,000 miles from the Earth. Okay. And it's actually sometime within a few hours, before or after now, I think maybe a little later today, it's going to be as far as it's going to get from the Earth. Then it's got its energy. It's still moving away, but the Earth is pulling on it, the moon's pulling on it, slowing it down. So eventually it'll lose the energy it takes to get up here. Okay, and it'll start falling back. And they'll fall back near the moon and so forth. Okay. And that'll loop the moon another time and then come back to Earth. This function tells you that if you move twice as far, you get 1/4 as much. Here's your square. Okay, you know, you move from 1/2 to 1, that's twice as far. You go from 4 down to 1. This is 1/4 of this, right? Now you move to twice this value, you get down to 1/4 of this value. Okay, so you move twice as far, you get 1/4 as much. It's just like this, but it's 1/4 every time you move twice as far. So you're you got twice the X value, you get 1/4 the Y value. Because X2 equals 2X1. And 1/X2 squared divided by 1/X1 squared equals what? Well, it equals 1/X2 squared times 1X1 squared over 1, just like before, except these are squared now. Nothing squared, we can say that that's equal to X1 squared over X2 squared, which is X1 squared over 2X1 squared. Now this is just like what we did before, and you don't see it on the board anymore. It's covered it. But actually, we don't need this there anymore. This is just like what we did over here, except we're using the 1/X squared function instead of the 1/X function. Here we use the 1/X function, which gives 1/X2 divided by 1/X1. Here we're using the 1/X2 x squared function, the reciprocal square function. And we're getting 1/X2 squared divided by 1/X1 squared. And by series of simple steps, that's X1 squared over X2 squared. We replace X2 with 2X1, just like we did over here. So can we simplify this fraction? Okay, so it's like what we did over here. we're gonna write that as, well, first of all, we're gonna simplify by doing square here. We're gonna get 4x1 squared, because of course you gotta square the 2, you gotta square the x1. And we could write that as 1/4 times x1 squared over x1 squared, which is just 1/4. Okay, so this shows that if I go twice as far, I go 4 times closer. Okay. So now, if I've got a point on this graph, let's put a point here. But here's how far we are. And if we go twice this far, we get down to 1/4 as high. So, well, let's see, here's where we are here. Imagine what twice as far as we are. Subdivide this and subdivide this. What's it for here? If we go twice this far, maybe we're out here. We get 4 times closer, so we'd have to subdivide this in half and cut that in half. It's going to give us a point out here. It's getting pretty close already to the x-axis. Now, if we go twice as close to the y-axis, we're going to go 4 times as high. Well, 4 times as high is actually going to be too high. Okay, and we go twice as close. We go 4 times that high, up about to where I can reach the slam dunk of basketball. Okay, I'm never able to slam dunk a basketball. I get my hand that far over the rim, but back in those days, basketballs are too smooth to grasp, and I couldn't get it to go over the rim. Well, they're a good basketball player. Probably average or a little better than average jumper, but nothing to brag about. Okay, anyhow, you understand what I'm saying. You get up there pretty high, and then you go 4 times that high, which is a fairly good sized tree. Okay, so this thing takes off really fast. It's got an asymptote with the y-axis. It's got an asymptote with the x-axis. Okay. Same thing. Okay, well. Now, the whole thing that my original goal here, although it changed when I started talking about the geometry of this thing, and I realized that, yeah, we could review a little bit of algebra. Okay. And that's actually pretty important. And even better, see how a little bit of algebra gives us insight into these graphs and into the behavior of these functions. Because again, that spacecraft is out there near the moon, and these functions are governing everything it does. This governs its energy, and this governs the forces. Okay. Okay, well. What's the value of this function going to be at 0? When x is 0.